Hello, good afternoon everyone. So welcome to another episode of running Keras and Tensorflow on Rstudio. Today we're going to focus on CNN. So CNN, if you don't already know, it stands for Convolutional Neural Network. So instead of just a simple feed-forward neural network like we demonstrated before, CNN tries to scale a big image down into a smaller array and then extract even features out of it. So it's very confusing when I say it like that. I'll show you an example later. So what it does very well is actually image recognition and image classification. So I'm gonna use image classification as the example today using the Cifar dataset. So before we go into CNN theory, let's go into the Cifar dataset first. So Cifar 10 dataset is developed by one of the University of Toronto, if I'm not wrong. It's hosted on their site anyway. So it stands for image index database that have 60,000 image with 32 times 32 pixels each and with 3 color channels. So they're not a black and white image, they're color image, which is why the total dimension for each of the input is actually 32 times 3, because every pixel has 3 color each, RGB, or red, green, blue value. So there are 10 classes in total. There are airplanes, automobile, bird, cats, deer, dog, frog, horse, sheep, and trucks. They are mutually exclusive. There's no overlapping between automobile and trucks. They're completely different, completely unique, and completely within their own label. They will not cross label. So there will be no cats that look like a deer. There will be no dog that look like a frog, and so on. So they are split into training and testing. So there are 50,000 for training, so 5,000 times 10, and then there are 10,000 for testing, which is 10 times 1,000 each. So just to simplify and summarize the whole thing, you have 5,000 image of an airplane for training, and another one you use for training. So you use for testing, that one we just ignore that. So every single classes over here has 5,000 image that you can try to train on. So next we go into what is CNN. So what is convolutional neural network? So Computerphile has an excellent video explaining the theory and ideas behind blur and filters that uses kernel convolutions and so on. So if you have the time, go away and watch it. I'll try to link it down in the video description below. But what it does is that you are trying to apply a smaller filter onto the image and try to scramble it around. So here we have one example. So the image input is here. So it's only a 3 by 3 grayscale image with 1, 2, 3. Right, it's a very simple example. So you can imagine your image will be exactly like this, but a lot bigger inside. So you know, right, your digital image is just a collection of pixels. So if you scale it down enough, it will actually look somewhat like that. Okay, so you have 3 by 3 pixel and only 1 layer. So imagine Cifar, we have 3 layers. Same concept applies and so on. And we have kernel. So you can see 1, 2, 3, 4 stands for 4 process on the same image. That's why they're the same. Same with the kernel, there are 4 processes of the same kernel. So this is your input is here and your kernel is here. So don't mistake it as different thing. They're just step 1, step 2, step 3, and step 4. So let's look at step 1 in particular first. Okay, in step 1, the green color is the area where you want to apply the kernel on. So we're applying 1521 onto 2132. Okay, so let's simplify a bit. Let's just put our kernel as 1111. So that is actually 1111. Okay, sorry for the keyboard noise. Let's just simplify a little bit down. Okay, so what does the processing means that for kernel convolution, you're trying to multiply the original value. So 2 times 1 equals to 2, and 1 times 1 equals to 1, 3 times 1 equals to 3, and 2 times 1 equals to 2. So it's going to be exactly the same. So in a lot of image computer science, this is actually called mean blur because it will actually blur the product to a certain extent. So the first convolution over here will become the first output on the pixel. So that would be usually the averages of the 4 pixels or any output within the kernel convolution, or you can run an average and so on. So it all depends on how do you set your parameter. So in this case, we are running a maximum. We're running an average from the kernel convolution. So let's do the second one, which is 1, 1, 2, 2. So we inherit the same pixel from below, and then this one will be the average of the second convolution. So it's 1.5. So we also inherit this to the bottom. Okay, so let's try the third part, which is we're trying to do it on this area of the image. So it's 3, 2, 1, 2. Okay, so we average the thing from 3, 4 of them, we get 2, and then let's try the last part. So this is 2, 2, 1.5. Okay, let's try to the last one. So it's 2, 2, 2, 1. Okay, so this processing. So the last one we are trying to do averages the 4 over here. So in this case, our output will be 2, 2, 1.5, 1.5. Okay, so if you do this many times using many different kernels, we'll be able to get many different output and so on. So let's try to do a computational formatting just to have a concept of how it works. So we're running a convolutional formatting from high to low. So you can actually see that the left side of the original input has a slightly value on the left side. Same with our output. On our input, there's a slightly lower value on the right, and we'll actually output it on the right. So in this case, you can see that our output is 1 pixel smaller on the left on the side, 1 pixel smaller on the side compared to the input. So our output is slightly smaller output because when you're doing convolution, every 4 will become 1, and there's some overlapping, but overall it will actually reduce the total number of pixels you have compared to the output. So you can do some padding. There are many ways to do it, but in most of the machine learning application, we do not do that. We are trying to scale down the image in one way or another anyway, because if you feed your whole image to a neural network, it's going to kill your computer RAM. So let's go to our script directly now. So there are several libraries that you need to import, and I could not run this in real time because I realized that I'm using my NVIDIA graphic card for the video processing, which is the video you're watching now, and I cannot run CUDA on the training network, so they don't run together. An extremely first world problem, I know, but I cannot show you in real time how these run. Where I can show you how to import the library though. So the first thing is you have to include 5 different libraries. There are TensorFlow, Keras, StringR, readr, and Per. So they're used for most of the. So StringR is used for string manipulations. readr is used to read the data in. So these two is StringR and readr is used to read the data into the environment, which actually we don't need it here, but I'm just going to tell you why later. So Per is used for pixel manipulations, data manipulation, and image plotting. About Keras and TensorFlow, you know what they do. So the first thing is to input the data set. So if you already have Keras and TensorFlow installed on Rstudio, you can just run this command to import the dataset directly into an object called Cifar. So you can, if your internet is really slow, because it's a 700 megabyte object, so about 150 megabyte to download. So if your internet is quite slow, you can also download the data over here and try to load it into environment using read lines, but it's a lot more janky, and sometimes it works, sometimes it doesn't. I'm not sure why is it so, because there's certain processing you need before you can do. So for simplicity's sake, you can just run this and leave your computer there for a while so that you get the data set in. Okay, so for the class name, we have 10 different classes, 1 to 10. 1 stands for airplane, 2 stands for automobile, and 3 and so on. So if you look a little bit at your data set here, we have 50,000 for our training, as mentioned earlier, 10,000 for the testing. So in this case, the dimension of the object is 32 times 32 times 3. So exactly the same as what we expect earlier. While the Y is only 1 dimension because it's only 1, which stands for airplane, 10 it stands for truck, and 4 is stands for cat, and so on. This is why your output label only have 1 dimension and 1 data value. Okay, so the index is 1 to 30 because we're trying to do a little bit of data exploration, try to see if we have load the correct data set or not. So in this case, the par and the per code and script here just try to plot the first 30 of input and output onto the plotting window over here. So you can take a look at a frog looks at a frog, a bird looks at a bird, a frog looks at a frog, a bird looks at a bird, and airplane looks at airplane, and so on, just to make sure we do not have the order wrongly put in the wrong place, and then everything get messed up if you do that. So just make sure that things are in the correct place, in the correct order, and so on. Okay, so the next one is actually to build our actual Keras model. So this we are using a really deep neural network. So there's two parts of this. The first part is actually the convolutional kernel part. So in this case, our kernel size is 3 times 3. So in this case, it's a 9 pixel value. So we have done from our Google Sheet just now that our kernel is 2 by 2. So in this script, we're running it in 3 by 3. So you're free to adjust the size of that, and every size has different consequences, so that if you have a smaller kernel, it's able to extract a feature from a smaller area of the plot, but also it might be overfitting on the fit. It might overfit the thing, so it's also creating a lot more calculations and so on. So there are ways that you can run around it, mess around it, and try to see what happens. That's the best way to learn what it does. Okay, so the activation for all our control, every intermediate layer or our hidden layer is using ReLU, while the output is using softmax. So let's go through the line, the parameter one by one, just in case I miss out anything. So the filters number is 32, means every single processing has 32 different kernels, each kernel 3 by 3 each. So in this case, you are generating 32 output per layer. So this layer will generate 32 output, each with a transformation of kernel that is 3 by 3 in size. I don't know if that is easy to understand or not. So in this case, we're using one kernel 2 by 2 each. But when you do machine learning, one kernel is never enough. So maybe this kernel is trying to blur the image. The other kernel is trying to extract edges. The other kernel is trying to detect darkness, contrast, and so on. So they will do different things. So there are 32 different of them applying on the same image. So every image will generate 32 of them. So this frog, this one input value, one image will generate 32 different objects from this layer alone. So we have 32 times 50,000 over here. So we have generated a lot of data set within the layer. Okay, so the input shape of course is 32 times 3 because that is the size of the original input that we get from Cifar, while the activation is ReLU, which is stand for Relified Linear Unit. If you actually don't know, we have a very nice picture here that I can show you. ReLU looks somewhat like this, so you can actually download this on the internet somewhere. I'm not sure where they got it. I'll try to link it down in the description on the page and so on. Okay, so in this case, once you're done the first layer, let's go to the second layer. So the second convolution layer is very similar, except that instead of 32 filters, we increase the size to 64. So every single output again will generate 64 different outputs. So we will have a lot of them. So every image now we have 64 different sub compartmentation, different features, 64 different features per image input. So since it's getting a little bit too big, we're trying to scale down the pixel size a little bit. So in this case, the max pooling layer is trying to pull a filter which is 2 times 2 in pixel and trying to get a maximum. So what does that mean is that if you have an output which is 1, 3, 4, 4, 5, so we're trying to get us 2 by 2, and we're trying to get only the maximum. So this effectively turns 4 pixel into 1 pixel. So this will massively downscale our image and only highlight the feature that we want. So that will remove a lot of, let's say, dark area, those that we don't care. So we only take the bright or the bright color value onto every single of our image, and all the dark one, we just ignore them. Okay, so say because we're using ReLU, you get the idea. So the next one, of course, is another convolutional layer, which is 64 unit, 3 times 3, very similar, and another maximum pooling unit. So this is our convolutional network layer for the first 5. And then we have another conventional neural network layer, which is having 256 neurons as input and 10 neurons as output. So if we run the summary model over here, you can see that this is our 9 layers of our neural network, where the first is we'll take the image and generate that all the image into 30 pixel times 32 pixel with 32 unit each, because we have applied 32 filters per image. So why is it 30-30? Because we lose one pixel on the top and one pixel from the bottom because of the kernel convolution that we did, similar to why we lose out one on the right and one on the left. Similar concept over here, just that if your kernel is bigger, you lose way more on the side, if that makes any sense to you. Yeah, you kind of try on the paper, you get it. So if you have a 3x3, you lose one pixel here and one pixel there, or 2 pixels on the side, if you want to understand it like that. So then the kernel convolution, again, we lose 2 pixels per side, and then the max splitting layer will actually effectively half the size of, actually it will make the size only 1/4 as big. So 24 times 24 becomes 14 times 14. So you make every 4 pixel into 1 pixel, so that will reduce our memory size, and most of the features that are not highlighted are usually useless. So we throw away those things, and we do similarly on the convolution layer, and we do another pooling layer, and we flatten the neural network. So what does a flatten means is that if you have an array, you can't fit an array into a neural network that easily. So every time you have an array of value, you can just take the first layer and lay it down by the side. So instead of a square, you get a line. So that changes our 2D shape, 2D matrix array into a vector, where we can easily fit the vector into our next layer of neural network, if that makes any sense. So I think I've talked about that in my last video. So yeah, you just basically turning a matrix into a vector, where then you can fit a vector easily into a neural network and so on. So, and then you have the dense layer, which is the same neural network for the next 4 layer, which down from 256 to 128 to 64 to 10. So this will slowly, gradually reduce our features into the things that we want, and that will actually pass it to the last output layer, which is only 10 neurons big. Why 10 neurons? Because we have 10 different labels. So in this case, if our output neurons, so the 10 output neurons will usually output the probability of if the image that you input belongs to that class or not. So if neuron 1 lights up a 1, everything else is 0, we know that it's an airplane. So if neuron 4 lights up a 1, everything else is a 0, we know it's a cat. And if neuron 10 lights up and everything else is dark, we know it's a truck. So if neurons 2 and 10 lights up, we know that 2 and 10 lights up, we know that is somewhat between a motormobile and a truck, but we don't know which one is them, so we cannot make sure. So in this case, we usually label that and misclassify, and we try to retrain the network again. But again, we also don't want to make it super duper accurate, because that usually result in overfitting, and you can't generalize the concept. So the last thing here is actually the last two things is the model compile, and optimizer is Atom, while the loss is sparse categorical cross entropy, and the metric is accuracy. So the optimizer and loss will be very dependent on the data set you fit in, and there's no correct way of doing things. It's just that you have to make sure you understand, are you doing a regression or you're doing a classification. So in regression, so we are doing a classification here. So Atom and sparse categorical cross entropy is alright for the purpose. But if you're running a regression, you might want to look into things like mean square error or mean absolute error, where it takes all the sum of the errors and try to add them together. So that is commonly used for the regression analysis and so on. So the last one is just a model fit, which I cannot run because you can't run OBS and then run the training at the same time. But I pre-run this before with only 5 epochs. So as you can see, because we set our validation split at 0.2, so 80% of our data will go into training, while the 20% will go into validating that our result is somewhat correct. So that's why we have 50,000 total input. So 40,000 will go into the training, while the last 10,000 will go into validation. So we have 5 epochs over here. So the meaning of 1 epoch is that the whole data set that you put in, if the model runs through the whole data set once, we call it 1 epoch. And every single epoch by the end, it will actually run a validation steps. So you can actually change the number of validation you want to run, but we're going to run 1 over here just for simplicity and for the understanding. And it is also the default of the of the program. So the model fit has a very specific syntax. You have to fit X as the testing data. In this case, the Cifar train X, which is the one I pointed out earlier, and Y is the training label. So Y is the Cifar train Y, and so on, as I pointed out earlier as well. So we're running only 5 epochs. You need to run this for at least 10 to 50 just to get an accurate answer. As you can see, the accuracy I get here is only 75%, and you can obviously see that the training is not complete, the loss is still gradually reducing, the accuracy is still gradually increasing. You still need to train this until it reaches either a stabilization in your training accuracy or your valuing accuracy. So you can use a callback, which I'll demonstrate in the next video that I'm gonna make. But once you run all this, so I'm also using multiprocessing to use multiple CPU or GPU and so on. Multiple CPU actually, just CPU over here because I'm running CUDA. So that would actually speed up a little bit, and it will actually give you accuracy so on. And I believe that's it. So that's basically how you run a CNN. And if you want to have, let's say the prediction is already 20 minutes long, so I'm not gonna continue to run on the whole thing. But if you do want a prediction, let me know. We can actually run another prediction as a part 2 of this video. For now, just to recap the whole thing, we're running convolution network on Cifar data. So Cifar 10 is a data set with 60,000 image with 10 classes. We're trying to feed the image in and get a label using CNN convolution neural network. So CNN actually runs a kernel onto the original input, and for every convolution we output one value. So that will usually reduce the number of pixels that we have compared to our original input, and we get a slightly simplified output with certain features. So if you change the kernel, you also change the output. So if you have 1, 2, 2, 2, the kernel, the output of this convolution is gonna look very different. So we're using one kernel here, so we get one output. So if you have second kernel, you will get a second output. You have third kernel, you get a third output, and so on. So in our overall script, we have 3 layers of convolution with 32, 64, and 64 each, and then we feed the output into a neural network, and we finally get a probability of the image being in each class based just by which neuron actually lights up by the end. So I believe that is everything about CNN. We'll see you in the next video. Bye. Yeah, so let me know if any further question or you do need to second part of CNN. Bye.